All right, so we are going to look at part 2 of cell respiration. So we're looking at the first two processes in this, which is glycolysis, and then the next is the Krebs cycle, also known as the TCA cycle, also known as the citric acid cycle, also known by my biochem professor in college as the mighty wheel, because it's really scary. But like I said in the first video, all you guys really need to know are the inputs and the outputs of these processes. You do not need to memorize every single step. You get no brownie points, you get no stickers. Do not kill yourself trying to memorize every single step. Know the in and the out for every step. So with that being said, we'll get started. So glycolysis, once again, that word glycolysis is sugar splitting. This happens in the cytosol of our cells. So it does not happen in the mitochondria yet. We're not even headed in the mitochondria. It's not even a gleam in our eye at this point. We are simply splitting sugar from a 6-carbon molecule of glucose, so a 6-carbon molecule, to 2 3-carbon molecules. So we have one 6-carbon molecule going into 2 3-carbon molecules of something called pyruvate. It's also known as pyruvate acid, but just pyruvate. We call this the most ancient form of energy capture because bacteria can do this. And the reason why they can do this in the cytosol, why it makes evolutionary sense, is because bacteria don't have mitochondria. So this is how bacteria need to actually get around. For every 1 glucose molecule that they eat, they make 2 ATP. This is very inefficient, extremely inefficient. It is like 50 times worse than using oxygen and using a mitochondria, but it's what they have. So bacteria do glycolysis because you do not need a mitochondria yet. So the summary of the, oh my gosh. Okay, so glycolysis summary is we have to invest a little bit of ATP. If you've ever heard the old adage, it takes money, make money, right? You have to invest a little bit of ATP. So with our glucose, it takes energy to actually break that molecule. But in the next phase of glycolysis, we get some energy payoff. So if we're putting in 2 energy dollars, we're getting out 4 energy dollars. And we're also getting 2 NADHs. So that is a reduced molecule because we've added a hydrogen to it and we've made 2 pyruvates. So down below, let me move myself so I can point. Right there. That's what you guys need to know for these steps is the energy payoff. So out of 1 glucose, we get 2 pyruvate and 2 water. 2 ATP go in, we get 4 out, and we get 2 NADHs as well. So how is the NADH recycled to NAD+? What happens is another molecule has to accept the hydrogen from NADH. In aerobic respiration, what happens, and your POGL does a really, really good job of outlining this, is in glycolysis, NADH gets a hydrogen from the glucose molecule. And then that NADH shuttles, it's like a taxi for hydrogen, it shuttles it to the next process. So we are able then to use that hydrogen to turn a pump. And that's aerobic respiration. However, in anaerobic respiration, we have to make acidic counterparts. Remember, hydrogen is acidic in and of itself. So if we are doing aerobic respiration without oxygen, we have some toxic byproducts. Ethanol fermentation, also known as alcoholic fermentation, and lactic acid fermentation. So lactic acid and ethanol are both very, very poisonous to our cells, and then our cells have to get rid of that toxic byproduct. So in bacteria, basically what happens is a pyruvate then gets broken down into ethanol and CO2. This is the reason why we can actually make carbonated alcohol. This is how beer gets its carbonation. When they're making wine and different things like that, that CO2 gets released from that process, so you don't get like bubbly wine or anything like that. But I mean, single-handedly, this process is what made Wisconsin a state. So woo, alcoholic fermentation. It's very, very important to our state and our economy. It's not only important for beer, it's also important for cheese. Swiss cheese is made with a similar process as well. And that's the bubbles in that cheese are a byproduct of the bacteria that lives in the cheese. They give off carbon dioxide in alcoholic fermentation. Down below, right there, animals actually do lactic acid fermentation. So this is us, this is people. So when we don't have enough oxygen for this pyruvate to enter the mitochondria to go into the next cycle, what happens is we turn that into lactic acid. So in order to oxidize our NAD back or NADH back into NAD, we have to make lactic acid as a toxic byproduct. And you can feel that if you do like a wall sit, you can feel that buildup of lactic acid because you don't have enough oxygen in your cells to actually like catch up to what your energy needs. Lots of different types of cheese and yogurt are also made with this. So we don't think about cheese as having like bubbles in it. That'd be really, or I'm sorry, not all cheeses. Some cheeses do use the alcoholic fermentation above, but like cheddar is made using this lactic acid. Same thing as yogurt. We don't think of like bubbly yogurt. That'd be really gross. So those are used, are made with lactic acid. Okay. So after we've made our pyruvate, your body has two choices. If there's oxygen, then we go to the aerobic route. If there's no oxygen, then we go to our two fermentation routes. So our pyruvate, when there's oxygen, it will then go into the mitochondria to the Krebs cycle. However, we have something that is called trimming. It's also called the link reaction. It's called both trimming and the link reaction. So what happens is pyruvate gets oxidized to acetyl coenzyme A. So here we have a transport protein. The pyruvate goes through the transport protein. CO2 is released, so it gets oxidized. We make another NADH, and then we have a coenzyme come in that binds with everything that's left. So now we get acetyl coenzyme A, acetyl coenzyme A. So we have a 2-carbon sugar now that's going to go into our next reaction. So all you guys need to know about this, it's sometimes called trimming or the link reaction. And we have to mess with the pyruvate a little bit so it can actually go into the next cycle. And now the mighty wheel. So this is probably the simplest image that you will ever see of the Krebs cycle. This is where most of our CO2 comes from. So I always like to say when we inhale, that's our aerobic respiration that actually feels the last process in this. When you exhale, CO2 comes out. That's the Krebs cycle. So the Krebs cycle makes most of our CO2 in this whole process. Basically what happens is our pyruvate through that trimming reaction or that link reaction gets converted into acetyl coenzyme A. That then will enter the mighty wheel, okay? Once it enters the mighty wheel, it goes through a whole series of chemical reactions where CO2 is made, NADH is made, we got some ATP that's made, you have some FADH2 that's made, and this whole process cranks twice for every 1 glucose. Remember, because 1 pyruvate is half of a glucose, so the wheel cranks twice for every glucose molecule. So this is what you need to know. The Krebs cycle produces 8 NADH, 2 FADH2s, and 2 ATPs. So all together with our ATP that we made in glycolysis, we only have 4 ATP. We're not much more efficient than bacteria at this point. The last part is the electron transport chain. This is the part where we really need our mitochondria to work, and this is the part that sets us apart from bacteria. Just this for most people. This is the only thing that sets you apart from bacteria. And this is where we're going to see where all of that NADH went, right? So the reason why we need the Krebs cycle is basically to make these two things, NADH and FADH2. We need these electron carriers to pump the last part of our cycle. Before we move on, just to sum up once again, glycolysis makes 2 ATP, the Krebs cycle makes 2 ATP, so we need to go on to the last step. So we will pick up that next time.